We are?
Let's see if I can full screen this. Cool. Okay. That works. All right, cool. All right, so hi everyone. I'm Maddy Bowers, and today I'll be presenting some joint work with Alex Lev and our advisors Vikash, Josh, and Armando. So let's start by thinking about how we as humans might approach this rule induction problem. So what's a rule that describes how each output list on the right here is computed from the input list on the left? Well, the output and input are the same length, so it might be some sort of element-wise computation. And if we look more, we might see that some of the outputs are just incremented versions of the inputs. 3 goes to 4 and 7 to 8. And actually the ones that aren't incremented seem to be decremented. And after looking at this for a while, we can figure out that the rule is that the even numbers get decremented and the odd numbers get incremented. But let's look at how a traditional program synthesis system would approach this. So our goal is to find this rule at the bottom, this program representing the rule at the bottom. And a top-down synthesis approach will basically start with a whole that represents an unfinished program. And at each step, it'll look at the possible ways of expanding that whole. So you might, for example, expand it to be a filter with a random predicate over your input list. Or it might be a map with a random lambda. Or it might be something like a cons with a random head and tail. Now, a top-down search will then recursively explore this combinatorial space of programs. But importantly, you can't actually execute these partial programs until they're complete. And so only then can you figure out if a program's correct. Now, looking back at this point, at this filter, if we studied this, we could actually realize that no matter what the predicate is here, this branch of search cannot bring us to the solution because it can only produce subsets of the input list. And this kind of pruning is essential to making efficient top-down search, and there are lots of different approaches that essentially focus on pruning in these kinds of situations. And we're basically going to look at how this kind of pruning can fall out naturally from taking our probabilistic approach along with some other benefits that we get. So in our approach, instead of thinking of these as programs with wholes, they're going to be probabilistic programs. And they're going to use randomness as a stand-in for logic that we don't yet understand. So for example, we start with this program that samples a random list that has a geometrically distributed length. And importantly, we can actually evaluate the marginal likelihood of our outputs, of the marginal likelihood that this program produces our observed outputs for a sense of how well it explains the data. So then we can go ahead and refine our program. So we can see if we refine it to a filter with a random predicate. This has likelihood 0, so that's recovering that pruning from prior work. We could also refine it to a map, which uses a lambda that samples a random digit. And that's actually quite a good explanation of our data because it explains why the input and output lists are the same length. And there are also various other expansions, like a cons, which doesn't reveal quite as much about the structure of the input-output examples, but still has some positive non-zero likelihood. So these likelihoods can actually provide us some signal for what the more promising branches of search are. Intuitively, the higher likelihood programs are already exploring or are already explaining more of the output examples through their program structure, so we should favor those branches of search. Now, that path of human-like reasoning that we saw earlier actually corresponds to a sequence of these programs, where first we refine to a map, as before, and then we refine the body of that map lambda to be a condition that sometimes increments the input element. We can further refine the random branch in that to a decrement to say some elements are incremented, some are decremented, but we don't know which. And then finally, we can refine it to a fully deterministic program. And of course, this process could be stopped early if you're trying to search for a particular probabilistic program. And as we're going, all of these likelihoods are getting lower and lower, or higher and higher. Now, in some preliminary experiments on list benchmarks, we found that this method with a very simple sampling-based search strategy can already show a couple orders of magnitude of improvement in the number of samples, number of rollouts needed to solve a task when you're just using this pruning based on likelihood 0 things. And then you even get a couple more orders of magnitude from doing the guidance based on more promising high likelihood branches. Okay, so that's the idea of likelihood-guided synthesis, but how do we actually calculate these likelihoods? So to set up the problem, we're going to work in a simply typed lambda calculus with conditionals. We're going to add the Y combinator for recursion, and some primitives for discrete randomness, and finally a handful of domain-specific primitives. Here are some dealing with lists and numbers. And our goal is to write this function constrain, which is going to take an expression and return the probability that that expression evaluates to a particular output. So this is actually similar to a problem that arises in bidirectional type checking, where, so as some background, when you're checking a type like a cons of E1 of cons of E1 and E2, and you're checking if it has a list int type, then you can check that E1 has type int and E2 has type list of int. So it just recursively decomposes quite nicely. But other times, like when you're checking the application of E1 to E2, there are many possible types that E1 and E2 could be. So bidirectional type checking switches to inferring the type of E1 and then uses that as a constraint to check the type of E2. Now, we're in a similar situation in likelihood evaluation, where, for example, if we know that, or if we want to evaluate the likelihood that, say, cons E1, E2 is the list 1, 2, 3, we can just check that, constrain the head element, E1, to be 1, and then constrain E2 to be 2 and 3, do those recursive calls to get our likelihoods and multiply them together. Now, if we have an application where E1 can have randomness and could return multiple different possible functions, we need to actually switch to something that we call forward evaluation, where we enumerate the possible closures that E1 could evaluate to, and then for each of those closures, we can constrain its evaluation on the argument E2 to have the output that we want. So to go through a few more examples, if we're trying to constrain, say, tail of E to 2, 3, we can first run this forward enumeration to get it to a cons constructor and then constrain the tail of that cons. And a really important thing here is actually our forward evaluation enumerates essentially just in weak head normal forms, meaning that it evaluates up to constructors, so you get all the possible constructors, but you keep the arguments as lazy, which means that the tail here is lazy, and we can actually terminate even in cases where E can be evaluated to an infinite list or even infinitely many different lists. As another example, constraining an if statement involves essentially constraining each of the branches, or constraining the condition, followed by constraining each of the branches to return the right values. Now, in summary, we have these two methods, constrain and forward, and they essentially mutually recurse in order to evaluate our likelihoods. Just to showcase in practice, on programs that, like this, that could generate infinitely many lists, constraining to a particular list, can terminate in around 3 milliseconds, where methods that need to do full evaluation will take several seconds and explore millions of lists. And if you double the length of this list, suddenly you need to look at 10 to the 12 different methods, or different execution paths, but we can still terminate in like 4 milliseconds in that case. And finally, in terms of things like map here, we can actually just define in terms of our other operators. So ultimately, this is in terms of the Y Combinator, and we didn't actually have to implement like specialized map or fold implement forward and constrain rules. Those just fall out of their implementations. Finally, as a quick note, we think that there's a lot of related work that's very relevant to this, but we don't fully understand the relationships and would love help from that, or from anyone on that. So for example, Hakaru's bidirectional disintegration algorithm, Eyeball's memoized variable elimination algorithm, several of the exact inference engines in Church, the idea of parametric inverses, and various other recent approaches to exact inference. And finally, there are also a handful of future directions we'd be excited to talk about, such as right now we require that there are finitely many ways to construct the output that, or we support infinite execution paths, but there need to be finitely many paths that lead to the outcome that we're constraining. So we're interested in handling infinite cases using things like at least getting bounds on the likelihoods, or handling continuous randomness, perhaps through sampling approximations, and also just better understanding where these likelihoods can and can't help in synthesis. And so would love to chat more. We have a poster later. Thank you so much.